Let me start by thanking the organizers for organizing this nice conference in this very beautiful place and to invited me. I work on the Riemann surface, which is a surface, definitely, on the Riemann sphere, and I do complex dynamics. And yeah, today I'm going to tell you about a joint work with Sean Bullitt that started in 2011, actually. And it's about correspondences in dynamics. The plan of the day, no, here, yes. The plan of the day is giving an introduction about rational maps, Kleinian groups, and Sullivan's dictionary, and speaking about matings, because what we do is mating quadratic maps, parabolic quadratic maps with the modular group. And this mating is a 2-2 correspondence on the Riemann sphere. So we will speak about where this thing started, a construction that Sean with Chris Penrose did in 1994 when they tried to mate quadratic polynomials with the modular group, the conjecture that they did, and the state of art. And then I'll speak about the results. And, well, and a kind of a parallel that we have between dynamics of quadratic polynomials and dynamics of this specific family of correspondences I will tell you about. And this is what it gave the title to the book. But, well, let's start with dynamics of rational maps on the Riemann sphere. If you have a rational map on the Riemann sphere and you start iterating it on each point of the Riemann sphere, a partition of the Riemann sphere into complement sets, which is dynamically meaningful. You can define the Fatou set as the set of points where in a neighborhood of which the family of iterates forms a normal family. And the Julia set is its complement. So if we want to look at an example, a very easy example, we consider the polynomial zeta go to zeta square. Every point with modulus less than 1 that lives in the unit disk, if you start iterating them, we'll start having modulus smaller and smaller and smaller and smaller. And they will eventually converge to 0, which is a attracting fixed point, super attracting actually. If you look all the points that lives outside the closed unit disk, when you will start iterate zeta to the square, their modulus will grow bigger and bigger and bigger and bigger, and they will eventually go to infinity. So the family of iterates is normal both inside the unit disk and outside the closed unit disk. These are the two Fatou domains. And the Julia set is the unit circle, where the dynamics is chaotic. If you are on the unit circle, you will stay on the unit circle. A little bit inside, you will go to 0. A little bit outside, you will go to infinity. A very important family in complex dynamics is the quadratic family, PC of zeta, zeta square plus z. Each polynomial of this family, actually, for each polynomial on the Riemann sphere, infinity is a super attracting fixed point. And therefore, it has a basing of attraction, which is defined as the set of points which are attracting to infinity, eventually. And in this setting, you can define the field Julia set for a polynomial PC to be the complement of the basing of attraction of infinity. So you have this bench of points that go into infinity and the points with bounded orbit. These points with bounded orbit are the field Julia set. The Julia set is the common boundary between the basing of attraction of infinity and the field Julia set. This is the example we saw before. the field Julia set for the polynomial zeta go to zeta square is the closed unit disk. This is the field Julia set for the polynomial zeta go zeta square plus c for c equal 1 over 4. This is for c equal 1 over 4 plus epsilon. And, well, this c is minus 1, and this is, don't remember exactly. But you can see that some of them are connected, and some of them are not. So you can define the Mandelbrot set as the connectedness locus for this family. This is the set of parameters C, for which Pc of zeta has a connected field Julia set. So this is the Mandelbrot set. This guy lives here. This guy lives here, the tip. This guy lives slightly outside. He lives here. He lives here. And he lives more or less here. If you have a quadratic polynomials on the Riemann sphere, when you are close to infinity, the C is kind of neglectable. The important term is zeta square. So you have a conjugacy called the Butcher map, which conjugates the action of your quadratic polynomial in a neighborhood of infinity to the action of zeta go to zeta square, which is the leading term. In the case your field in Julia set is connected, this conjugacy extended to the whole basing of attraction on infinity. And in the case your Julia set is locally connected, thanks to Carter-Theodori theorem, the inverse of the Butcher map extends to a semi-conjugacy of the polynomial on the Julia set to the doubling map on the unit circle. And this map will be pretty important later.
Are there examples where the Julia set is connected but not totally connected?
Yes. Just knowing the ones, none of these that I shown you, but yeah, there are examples. On the other hand, let's jump to another word, the word of Kleinian groups. We can consider PSL2C, the group of 2 times 2 matrices with complex entries and determinant 1 under this equivalent relation. And the Kleinian group is a discrete subgroup of PSL2C. If you have the action of a Kleinian group on the Riemann sphere, this action also divides dynamically, gives a partition of the Riemann sphere which is dynamically meaningful. And namely, it divides it in the ordinary set, the set of points where the action of the group in some neighborhoods of zeta forms a normal family, and the limit set, which is its complement. The modular group is a particular example of Kleinian group. It's PSL to zeta. So the entrances in your matrix are integers. And it's finitely generated, and we can take the generators to be tau 1 of zeta, zeta plus 1, and tau 2 of zeta, zeta over zeta plus 1. And here you can see the tessellation of the modular group on the upper half plane. This is stolen from Wikipedia. And it will be very important later, the fact that a modification of the Minkowski map conjugates the action of the generators of the modular group on minus infinity 0 to the doubling map and on 0 plus infinity with the halving map. I'm lying. It's more complicated than this. You can just think about the fact that tau 1 of zeta doesn't leave descent invariant, right? I mean, the image of minus infinity 0 is minus infinity 1. So it's actually. Huh?
What is it?
It's this map. I didn't want to enter these details, but I kept it just in case somebody asked. Exactly this homomorphism, which sends a real number represented by a continuous fraction, so she's 0, she's 1, blah, 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 to the binary number obtained by 0 dot she's 0 copy of 1, 0 copies, she's 1 copy of 0, x2 copy of 1, and blah, 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 blah. So it sends 0, infinity to 0, 1. And then actually we consider not just the Minkowski map, but the 1 minus the Minkowski map of minus x. And this one is the one that conjugate, that we work on minus infinity 0. And actually, when I told you that it's more complicated than just these two maps, it's because we happen to have these 6 commutative diagrams. Then I won't go through. It's kind of proof by intimidation. It's complicated, believe me. But it works. This is to say that, let me come back. The action of the modular group on the real line fits the action of the doubling map here and the halving map here. This will be crucial.
How can an action of two generated group action be conjugated to an iteration? Or you're going to interject
Well, I mean, you have to restrict, depending on the domain, you have the Minkowski map that conjugates T1 to the doubling map on this. Then, I mean, if you go, if you want to conjugate it to to tau2, you go to this subset. I mean, it's complicated, but it works. Okay. So, the action of rational maps on the Riemann sphere and the one of finitely generated Kleinian groups on the Riemann sphere are pretty much kind of similar. And Sullivan realized it in 1985, 1990, and wrote what is called the Sullivan dictionary, that it's a set of correspondences between these two words. So, rational maps and finitely generated Kleinian groups. The Fatou set for a rational map is actually defined in the same way as the ordinary set for a Kleinian group. The Julia set, which is its complement, where the dynamics is chaotic, it's defined as in the same way as the limit set in the world of Kleinian groups. And actually, he expoiled these similarities, borrowing ideas from the world of Kleinian groups for proving something that was stunning, astonishing, a revolution in complex dynamics, that is the non-wandering domain theorem. I don't want to enter this, but it's just for saying these two words are much more related than what people thought at the beginning. And this is why we started thinking to mate them. And in order to tell you what it means, I have to tell you what a mate is. Very roughly speaking, a mate between two objects, let's say A and B, is an object which behaves on some invariant subset of its domain as the first object, and on some other invariant subset of his domain as the other object. Matings in the world of polynomials started in 1993 by Douady. And it happens that if you mate two polynomials, which are mateable, so not any polynomial, you get a rational map such that it has two invariant well, it has two Fatu domains, in which one is conjugate to the action of your rational map is conjugated to the action of your first polynomial in his field Julia set, and on the other set, the action of your rational map is conjugated to the one of the other polynomial. I just want to show you a video because I think it's more understandable than me speaking, if I manage. Yes. This video is taken from Cherita's webpage and shows the mating of two quadratic polynomials. And you obtain a rational map where in some part of its domains is conjugate to this polynomial on the field Julia set and on the complementary to this, the action of this polynomial. Opa, no, wait. Okay. And now, Control A, L. Yes, just one sec. And it happens that matings also exist in the world of Kleinian groups. It happens that you can mate two Fuchsian groups for getting a quasi-Fuchsian group. So, in this year, in the beginning of the 90s, it was the years in which the attention was very much drawn to these similarities between correspondences between Kleinian groups and rational maps. And Sean Bullitt and Chris Penrose started thinking, well, what about trying mating rational maps and Kleinian groups? Well, if you mate the two polynomials, you end up with a rational map. If you mate the two Kleinian groups, you end up in the world of Kleinian groups. But yeah, a rational map is not a Kleinian group and vice versa. So I mean, in order to this thing to be possible, we should find an object that is general enough that contains as subcases both rational maps and Kleinian groups. And such an object is a holomorphic correspondence. A holomorphic correspondence on the Riemann sphere is not a map, it's a multi-valued map, f zeta w, defined by a polynomial relationship, relation p zeta w equals 0. We just concentrate on two correspondences. So we consider a polynomial of degree 2 in zeta and in w. Their zeros forms an algebraic surface. Let's call it S. And zeta w equals 0. We can consider the projection on the Riemann sphere where zeta lives. And the projection on the Riemann sphere where W lives. And your correspondence, your 2-2 correspondence is this map. That to each zeta gets his preimages here and his two images here. And each point here has, well, two preimages here and then one here. So each point has two images and each point has two preimages. So they are kind of complicated objects, but the upside, the bright side, is that you can, if you have a rational map, f of zeta, p of zeta over q of zeta of degree, let's say, n, this can be written as a n-to-1 correspondence, where your polynomial is w q of zeta minus p of zeta, trivially. And if you have a Kleinian group, gamma, with generators, I don't know, gamma 1, gamma n, written this way, you can write it down as a correspondence, as an n correspondence, defined by the zero of these polynomials, which is the product of w multiplying by the denominator minus the numerator. Okay? So this is to say, this object is general enough for containing both rational maps and Kleinian groups. So, Sean and Chris started considering a particular family of quadratic 2-2 correspondences and plotting their limit set, making some numerical experiments. And they started seeing pictures like this one.
So what is the limit set of correspondence?
Let me, I will define later for this one, just a minute. They started making numerical experiment to plot a particular family, to see the dynamics of particular family of correspondences. I will define limit set later.
What is the dynamics of a family?
I will get there later, sorry. And they started seeing these pictures. And this picture looked like two copies of this Field-Julia set, one here and one here, with outside the tessellation of the modular group. So they're starting wondering, what about trying to make quadratic polynomials with the modular group? And they made this construction. Take two copies of your favorite connected and locally connected Field-Julia set. Mine is the one of zeta go to zeta square because it's very easy to draw. So you take two copies. You glue them at this point. So you basically take one and you turn the other of pi and you glue them together. And you define on the union of these two sets a 2-2 correspondence in the following way. You put the dynamics of zeta of your polynomials on the left Field-Julia set and the dynamics of the inverse of your polynomials on the right Field-Julia set. So now everybody here has two preimages, and everybody here has two images. So we need a 1-1 map going from this set to this set for getting a 2-2 correspondence. And they took this map to be zeta goes to minus zeta. So this forms you a 2-2 correspondence on these two sets. And you know that on the boundary of your set, here your map is semi-conjugated to the doubling map, and here to the half-field map. And then you take the upper half plane and you define there the correspondence defined by the polynomial, this polynomial, which is taking the generators of the modular group, zeta plus 1, and here there is a zeta missing, sorry. W zeta plus 1 minus zeta. It went out of this slide. So you consider the modular group here inside. And you know, because of all these the 6 commutative diagrams, that the action of the modular group on the negative real axis matching the action of the doubling map, and on the positive real axis matches the action of the half-field map. So what you do? You glue, by Butcher and by these Minkowski maps, your Field-Julia set with your upper half plane. You sent 0 to this point, and minus infinity and plus infinity to this point. So basically, you have these two sets, and you wrap around them the upper half plane, basically like this. And you obtain a 2-2 correspondence on a topological sphere. And they proved, well, they defined a mating between a quadratic polynomial and the modular group to be what you expect, a correspondence, a 2-2 correspondence that on some completely invariant open simply connected region, it is conjugated to the action of the modular group. And on the complement of this simply connected open set, this complement is made by two sets which intersect in a single point, and where on one of these sets the action of your correspondence is conjugated to a quadratic polynomial, and on the other one to the inverse of such quadratic polynomial. And the proof, the proof that actually in the paper where they made this construction, which is in Invenciones in 1994, they proved that for A equal 4, this 2-2 correspondence is a mating between a quadratic polynomial, namely zeta squared, and the modular group. Then Sean worked for a long time on this setting, and with Heisinski proved that for all A in this real interval, the correspondence, this family of correspondence, is a mating between a quadratic polynomial and the modular group. Yeah.
I can kind of see fairly clearly what you explained how to do the topological construction. You do something like have these two dynamics, you glue. So the problem here is to find this formula, is it?
Well, so why to get this formula? They wanted to find a candidate that could be such a mating. And the modular group, you can take for generator to have one of order 3 and one of order 2. And it turns up that this correspondence, you can write it down as correspondence, an order 3 rotation composed to an involution. So something of order 3 and something of order 2. This is why they ended up with this family. The problem is that explaining how this can be written as these two generators will take me a quarter of an hour, and I decided to skip it. But it's an important point. This is the candidate because they made some computation such that if there was a candidate that would have behaved like the modular group, it would have been this one.
Is there no relation between A and C?
Yeah, for A equal 4, C is equal 0. And for the other ones, yeah, you can find the other one, but yeah, you make some computation. You look where the critical point goes, and yeah, there is some relation, of course. Yeah. Okay.
So you got many times in your correspondence, you got many times the dynamic of the quadratic graph, which is embedded something.
You have basically you have the dynamics of the quadratic map and the dynamics of the inverse of the quadratic map.
But just once, you don't have that.
No, you don't have a million copies. No, just these two.
Unless from your definition, like really, you got only just these two dynamics that you're making.
Yeah, we consider just two correspondences.
But it's still all the sphere.
Yes. You have these two sets, and you wrap outside your upper half plane, and you get the whole sphere. Well, actually, these guys are defined on the Riemann sphere, yes. Well, this is the connectedness locus of your family of correspondences, which is the set of parameters for which the limit set is connected, and I'm going to define the limit set in 2 slides. But, I mean, this is the Mandelbrot set, and you can see some similarities. So when they plotted this picture, they started thinking, wait, maybe this set is homomorphic to the Mandelbrot set. A is the parameter of the family, yes. Yes, it's a complex parameter. It's this A, and it's complex, yes.
What is it related to C? Like A and C?
If A is equal 4, you have this correspondence, and this on this field Julius on this set, your correspondence is conjugate to the polynomial zeta goes to zeta square. So A equal 4 goes to C equals 0. But the homomorphism that sends this guy to this guy is still work in progress. We still didn't get there.
Wait, I think we're still on the real line.
Yes.
Because, so they prove something for A real. But then...
And then there is the rest of the talk.
Oh, I see.
So the conjecture that this family contains mating between the modular group and quadratic polynomials with connecting Julia set for all the parameters here in the connectedness locus. And that there was an homomorphism between this connectedness locus and the Mandelbrot set. With Heisinski in 07, they proved that actually for a lot of parameters here inside, there is a mating. What happens is that their result use polynomial-like mappings. So they need, I will get into this. This result use polynomial-like maps, and because of this tool, and I hope it will be clear in 2 slides, it cannot get the whole connectedness locus. So what is a polynomial-like map? Bon, a polynomial, we saw at the beginning that for a polynomial, infinity is superattractive, and the field Julia set is the complement of the basing of attraction of infinity. So if you take a disk, a topological disk, well behaved enough, about the field in Julia set, the preimage is compactly contained in the disk, because the dynamics outside the field Julia set escapes to infinity. So if you have, I'm sorry, I think it's not very seeable, black over on blue, so I will do it here. If you have the field Julia set of zeta go to zeta square, the complement is the basing of attraction of infinity, right? So if you take a topological disk about him, the preimage is compactly contained. And your polynomial, P0 of z, sends the disk compactly contained in the other to the bigger one. A polynomial-like map, it's this. Something, it's a, what happened? Sorry, okay. A polynomial-like map, it's an object that behaves like a polynomial on a neighborhood of its field Julia set. So it's the data of 3 things, one set, U prime, compactly contained in a bigger set, U, and a map F, sending properly and holomorphically your smaller disk in your bigger one, with a sum degree D. And Duady and Hubbard, you define the field in Julia set for these guys as the set of points that never leave your domain. And Duady Hubbard proved that every degree D polynomial-like map is hybrid equivalent to a degree D polynomial. Equivalence is hybrid if it is quasi-conformal and is conformal on the field in Julia set. D bar is equal to 0 on the field Julia set. So how to apply polynomials like mapping to this family, and how is the dynamics of this family, and how is the limit set defined? So it happens that for each member of this family, you have a disk, which is whose boundary is in this picture is the imaginary axis of the images of this disk. So here your dynamics is 1 to 2, and is mapped inside and inside and inside. In the complement is the complement.
So we open the sphere and we think Z goes to wherever Z goes.
We are taking this expression. Oppa. This is your correspondence.
Yeah, but then you project into the Z coordinate and see what W is.
Well, every Z has 2W according to this expression, yes. Exactly. So every Z here has 2 images inside. And on this complement, the preimage of this line is this line. And this is mapped 2 to 1. This is mapped here, and this is mapped here. Okay? And the backward limit set is the intersection of the preimages of this topological disk B. That is this left plane. So the dynamics of your correspondence on this part is not exactly the dynamics of a polynomial like map. Sorry. But it's the dynamics of what is called a pinched polynomial like map. You can see that you have, well, let's make it in red, so I will respect colors. See that this one is mapped in this bigger disk. And you have a pinching point. You don't have something nice as something compactly contained sent to something outside. So what you do with this object? Well, you perturb your correspondence in order to destroy this, which is a parabolic fixed point, and disconnect the 2 limit sets. So you get a backward limit set disconnected from your forward limit set. And when you disconnect it, the dynamics becomes the dynamics of a polynomial-like mapping. You apply polynomial-like mapping, you prove then that here the dynamics of your limit set is conjugated to the dynamics of a quadratic polynomial, because it's a polynomial-like mapping. And then, for coming back to this guy, you pinch them back using a pinching surgery that Peter Jasinski developed. The problem is that, well, I mean, it's not an optimal way. If for every time you have to, for each parameter, you have to perturb them, apply polynomial-like mapping, and then pinch back. It's not optimal. And actually, in '94, it's in the introduction of the Chris and Sean's paper, they wrote that to prove that our lambda minus and lambda plus are homeomorphic to the field in Julia set, we should have to extend the Duody-Hubbard theory of polynomial-like mappings to a theory of pinched polynomial-like mappings. This is a difficult technical problem. And it was a difficult technical problem indeed. It was my PhD thesis. And yeah, forget about the definition. It's very long and kind of unpleasant. So if we want to extend this kind of guys for guys who have a parabolic fixed point, what's the model? Well, if you start having here a parabolic fixed point, then you have an attracting direction and a repelling one. So your preimage here can stay inside, but here, it sticks out. And then, in order to separate the parabolic dynamics to the hyperbolic one, you can define dividing arcs here. And this is a parabolic-like mapping. I define it this way, not in the pinched way, because for a lot of technical reasons, even if I had to kind of discuss with a lot of people because this was the model in the head of everybody. But yeah, you define this object, and you define the field in Julia set for this object, the set of points that never escape this part of the domain. Because here the preimage of the parabolic part, God knows where it was.
So what is this part can you actually the smaller it is, the section of the arc?
The field in Julia set is here inside. This part, you call it omega prime. And the field in Julia set is the set of points that never leaves omega prime union the parabolic fixed point. Is the definition of this thing.
And these arcs, they're what?
These arcs are, well, forward invariant arcs. C1 on pieces. Yeah. Which divides your set in exactly this way. In the sense that, I mean, this omega prime is compactly contained in your range. And you know that you can always define those guys because you have fatu coordinates at parabolic fixed point, but I don't want to enter that. It's just a tool that we use for proving something else. So, if polynomial-like mappings behave as polynomials and are straightened to polynomials, parabolic-like mapping behaves like some family of parabolic guys, which is per 1, 1, the family zeta plus 1 over zeta plus a for a complex. Everybody in the family has a infinity as parabolic fixed point with basing of attraction lambda, which is completely invariant. So you can define the field in Julia set for these guys as the complement of the basing of attraction of infinity. Is exactly like for polynomial. Just infinity, now it's parabolic. The connectedness locus of these guys is called M1, the parabolic Mandelbrot set. And here is a picture, which I'm sorry because the black over blue is not very seeable. You can see it's very similar to the Mandelbrot set, just it doesn't have the cusp here. And here are several field in Julia set. And by a work of Carsten Petersen and Pascal Hoche, the parabolic Mandelbrot set is homeomorphic to the Mandelbrot set. And what I proved in my thesis is that every degree 2 parabolic-like mapping is hybrid equivalent to a member of the family per 1, 1. So we have a parallel of the polynomial-like theory. So, when we saw the difficulty of managing to get the result Sean and Peter had, because by the end of the talk, I'm going to manage to deal with the pointer. Something like, in order to prove that these guys are conjugate to polynomial, they had to perturb it for killing the parabolic fixed point, apply polynomial-like mapping, and then pinch back. Because here you have a parabolic fixed point. So we started thinking, well, this is not very suitable. It's not very straightforward. Maybe if everybody in your family has a parabolic fixed point, maybe you should mate these guys with a parabolic family and not with polynomials, which are hyperbolic. I mean, infinity is super attracting. So we started considering why, instead of considering mating between quadratic polynomial and the modular group, we define matings between these parabolic guys and the modular group. So we defined a mating, correspondence to be a mating between a rational quadratic map of this type and the modular group if the 2-to-1 branch here that leaves this guy invariant is hybrid equivalent to your quadratic rational map on your limit set. And when restricted to the complement of the limit set, your map, your correspondence, is conformally conjugate to the pair of Möbius transformation, tau 1 and tau 2, sorry, of the generators of the modular group. And we proved that, using parabolic-like mappings, that for every parameter in the connectedness locus, your correspondence is a mating between a quadratic rational map of this form and the modular group. And here are the pictures. This is the center of the component of the parabolic Mandelbrot set, which is the guy mated with, which is the guy corresponding to this one. This is A equal 4, that we already knew being hybrid conjugated to zeta square. But you can actually see that the limit set looks way more like this guy than a unit disk. Well, and it happens that it's the same way because I hate this pointer because the homomorphism between the parabolic Mandelbrot set and the Mandelbrot set is dynamical. Almost everywhere, actually, not at the primary point, but at this point it is. So actually, this guy is conjugate to z equal to z square. Well, here you see that here you see two copies of this guy, and we knew also this because I mean this guy lives in the real line. But this guy we didn't know because it's not living in the real line. And here you see that you see two copies of this Field-Julia set. And we are working for proving that this guy and these guys are homomorphic. I just want to say 2 words about the proof, just 2, because it's technical. What's the problem? The problem is that here you have a line which is sent, well, you have a neighborhood of this point, which is the pre-image of the parabolic fixed point, that is sent 1 to 2 here. So you have a disk here, which is sent to a half disk here, and is sent also to this half disk. So what's the idea for turning this guy to a parabolic-like mapping? Well, the idea is killing what's happening here by quasi-conformal surgery. You basically make a surgery to change your map in a neighborhood of this sector that gives you problem, on the sector that gives you problem. I don't want to enter details because it's rather technical, and I have kind of 5 minutes by now.
By killing, you mean you take it out and you glue in some particle form or something that will do what you want? Is that...
Okay. You know that this disk is mapped 1 to 2 here. So this guy is mapped
1 to 2 or 2 to 1?
1 to 2. That's the problem. If it was mapped 2 to 1, you will have exactly what you... Okay. Okay. Let me go slower. Sorry. Yeah. This guy is mapped on the big... let me get a bigger one. Okay. This part is mapped 2 to 1 here. But the problem is that this sector goes here inside and on the other side too. So you have a sector here which is mapped 1 to 2. And that's a problem because 1 to 2 is not a map. In particular, cannot be a parabolic-like map. So what we do? We kill the dynamics here. We do a quasi-conformal interpolation between here and the image here for killing something here and be left with a map. And the surgery is not that difficult. I mean, if this disk is sent here 1 to 2, it means that the pre-image here is sent here 2 to 1. So you can uniformize for this one being zeta to zeta square. And you just kill by quasi-conformal interpolation. You leave the dynamics fine on almost half a day. Well, there are problems because, of course, you want the things your structure to be invariant and blah, 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 blah. Technicalities. You can do it. It works. And you get that every member of the correspondence is a mating between some rational map and the modular group. And this is for the part 1. The problem is that you also have the part 2, because the fact that outside you have the action of the modular group is not that trivial. I mean, they proved it on the real line, but in general, it's way more difficult. Actually, what they had with Peter, the result that they had with Peter Isinski, it was concerned about the dynamics inside the limit set, and not the dynamics outside. So for proving this second part, we need to prove that restricted outside, your correspondence is conformally conjugate to the generators of the modular group on the upper half plane. So what you need? What you do is that we show that for every A in the connectedness locus exists a Riemann map that goes to this disk to a disk, so it can be the upper half plane. This is easy. But that such a Riemann map conjugates your correspondence restricted here to the generator of the modular group on the upper half plane. This is definitely not trivial. But the cool part of this is that our Riemann map plays the same role that for this family that the Butcher map does for quadratic polynomials. And yeah, this is the slide that gives the title to the talk. Because we have that, well, the Butcher map for quadratic polynomial with connected Julia set uniformized the complement of your field Julia set to the complement of the unit disk, conjugating the dynamics to the dynamic of the leading coefficient. And for correspondences, we have that our Butcher map uniformizes the complement of the limit set to the upper half plane, conjugated the dynamics of our correspondence to the one of the generator of the modular group. For quadratic polynomial, you have external arrays, which are I have 2 minutes. It's my last slide. Wow. If you have, well, let's make your Butcher map conjugates the outside of the filled-in Julia set to the outside of unit disk. And you can define on your dynamical plane external arrays, which are the preimages of rays of a constant argument. And well, this one I know that is here, and the other one, well, you have. I am not very good at drawing, but I mean, you just pull back by the Butcher map these straight lines, okay? And in our case, well, I mean, no. On the upper half plane, you have geodesics. And this plays the same role as external arrays in our theory. You can pull them back by the Butcher map. And periodic arrays land in the polynomial setting, and periodic geodesics land in our setting. The geodesics which are periodic, that they come back. Of the modular group. And in the polynomial world, every repelling fixed point is the landing point of a periodic array. And in our world, every repelling fixed point is the landing point of a periodic geodesics. This was very hard to get. And actually, for polynomial, you have that every repelling periodic point is the landing point. In our setting, we didn't manage to get periodic points because the argument uses Sturmian sequences and it's very complicated. But moreover, for quadratic polynomial, you have a Jacobs inequality. Yes?
So, if the repelling fixed points are landing points of periodic arrays and periodic arrays land, you need to assume that the set is connected, and what is the assumption for quadratic correspondences?
Well, if you are in the connectedness locus, your limit set is connected.
So that is the same.
Yeah. You have a Jacobs inequality in the case for quadratic polynomial, and we prove a Jacobs inequality in our case. And consequences, and you have that your mandible set is bounded, is contained in a disk. And thanks to the Jacobs inequality, we managed to prove that our connectedness locus is contained actually in a Lioun, which is actually something we need for proving this homomorphism, which is still work in progress. And thank you very much.